Welcome to session 15 in our series on electricity and magnetism. We're in part 2 now. In our last session, we learned about resistance. Basically, it's electrical friction. As we're trying to move electrons through our wires, they dissipate some of their kinetic energy as they're moving through the wire, and we have to reaccelerate them. To do that, it takes voltage. The formula that tells us how much voltage we need is right here. It's the resistance times the amperage equals the voltage, and I have voltage lost because that voltage is not useful for us. I mean, it's a necessary loss, but we'd like to minimize it. The other thing we learned in session 14 is that if we have this voltage that's required to push the electrons through, since there's amperage in this circuit here, the amps times the volts results in the wattage that's lost. Now, last time we were concerned about the heat that's generated if our wire is kind of thin for the amount of electrons we want to push through it. If we push too many amps through that wire, it can overheat and cause problems. And we learned about how the circuit breaker protects the wires in our buildings and keeps them from catching fire. In this session, we're more concerned with this voltage loss. Now we're going to use wires that are nice and thick. We don't have to worry about them overheating. So their diameter, here's the formula for resistance. Resistance equals resistivity times the length of the wire divided by the area. We're picking a wire that has a nice big cross-sectional area, enough surface. The resistivity is very low. But if L is big enough, we're still going to have an R we have to deal with, a resistance we're going to have to deal with. So what we're going to do is we're going to demonstrate how several devices, a hairdryer and a space heater, operate when they are connected directly to, let's say, an outlet in your house. And then we're going to add a very long extension cord. Let me show you on this diagram here. So initially, we will take the device. Here I've just got a hairdryer, but that could be the space heater or any device we're doing. And then we've got the meters. I only have one meter showing, but we'll have a voltmeter and an ammeter. And we will plug that directly into a 25-foot nice heavy-duty extension cord. We'll take measurements, we'll look at how much voltage is being applied, how many amps are being used, and how the device is performing. In this case, how much air is coming out, and perhaps get an idea of the temperature. When we're done with that, we will then disconnect from here and plug it in here where we have inserted a 500-foot long extension cord. Now that 500-foot extension cord is right here. Let me zoom in on that so you can see it, and then we'll zoom back out. We've got, a little too far, we've got 500 feet up and 500 feet back for a total of 1,000 feet. It's number 14 copper wire. And let's go back to the chart. We used this chart last time. We gave examples of different materials where the wire was 1,000 feet long. Number 14 wire, that determines the size of the wire. And for copper, it would be 2.5 ohms. So that would be the resistance of that coil that I just showed you. Now, to give you an idea of the order of magnitude, these devices are going to be operating at 10 plus amps. So if my resistance is 2.5 for that 1,000 feet, 500 up, 500 back, 2.5 ohms, that's the symbol for ohms, times 10 amps equals 25 volts. So that's the order of magnitude difference we're going to see between long extension cord or more direct plug-in to the wall. So let's get started. Okay, got the meters on. We're going to turn on the hair dryer on high. And let's go to a close-up here. Here you can see the 2 meters. And I'm going to jot down what the voltage and the amperage are. I've got 115 volts and 12.7 amps. Let's multiply that out. 115 times 12.7 equals 1460 watts. Okay, hold it right there. 1460 watts. Let's take another measurement. We would be concerned when we change this, will we be overheating or underheating? So I think you can see the numbers in there, maybe. I'll call them out to you. It's moving between 130 and sometimes hits 160. 150s and 160s. Okay, now notice how much air is blowing against our little flag here. It's almost parallel to this stick. And now we're going to insert the 500 feet of extension cord. Notice there isn't as much air coming out. Let's take a look at the temperature in here. I'm going to say 140 to 150. A little bit cooler, not a big difference, but there isn't as much air coming out. And let's take a look at the volts and the amps. So we got 91.4, 3, and 10.2. I'm going to ballpark this. It looks like it's about 920 watts. So the difference, I'll get hold of this where you can see it. 1460 was what we had, and now it's only 920. Sorry about the equal sign. Here and here. Okay? Now as long as this doesn't overheat, we're okay, and the only thing we're losing is you got to take a lot longer to dry your hair. And one other thing is we're wasting some power because the voltage that's available is about 115 volts. 115 minus 91, that's about 24 volts. 24 volts times 10 amps is 250 watts. So we're wasting 250 watts. $250 watts. I got you on close-up here. Sorry about that. Yes, 250 watts were being wasted, and we only had 920 watts of heat versus 1460. All right, let's do a similar experiment with the space heater. Let's erase this here. And everything's good there. We'll plug in the space heater instead of the hair dryer. Okay, and let's plug it in directly to the 25-foot cord and turn it on. You can see the little flag here being held a certain distance away from the, turn it a little bit, you can see, well, I want you to see the glow of the coils. And let's take a look at the power that's being consumed. 115 volts. And I'm going to round that up to 12. Which would be, let's see, 1150 plus 200. It's about 1400 watts, more or less. And kind of notice how far out this is, because there's a little fan in here cooling the box. We don't want the box to overheat, because even though it's radiating, it's also got a lot of convective heat gain inside the space here. Now I'm going to switch it and include the 500-foot extension cord. I think you can see a faint glow. I'm going to disconnect it and you'll see the difference. That's off. This is with the 500-foot extension cord. Okay, it's glowing right there. The fan isn't blowing quite as hard. Hopefully it's enough to keep the box cold. I don't know. I don't know how it's engineered. And now let's look at the power that's being dissipated in the heater. We've got 92.6. I don't know if I showed you last time what it was. I apologize. 92 point, well, it was 6 last time I looked, times 9.6. And that is on the order of 900. I'm just going to wing it. And so, here we go. 1400. When we stuck the extension cord in there, it's 900. And since we're going from 115 to 92, we're losing about 23 volts times roughly 10 amps. We're losing 230 watts. 230 watts in the coil, in this coil. Similar to what was going on with the hair dryer. Now we're going to do one more thing. And before I do, I'm going to give you an idea of what, let's go to this camera here. So think about a contractor who's building a building on his job site, and he needs extension cords to operate a bunch of tools. Might be some power saws. Let's zoom out a little more on that so you can see these. Yeah, you've got the hand power circular saws, chop saw, a compressor for the guys who are using the nail guns. And all of these might be operating on a single extension cord from the temporary power that's provided by the electric utility. Now if that wire is too thin, now we're not worried about heat, it's too thin and all of these are working together, the voltage is going to be too low and it's going to really slow the work down in some cases. In other cases it may actually result in equipment being damaged. I'm going to give you an example here of how poorly something can operate when the voltage is too low. We're going to use the space heater because it's quiet, and then I'm going to turn on the compressor. The compressor is already up to pressure, okay? It's up to pressure, and so it's going to have to work hard when I turn it on. And we are going to operate it with the 500-foot extension cord. That's good, that's good. We've got 118 volts. And now we turn this on. And we've dropped down to 92. We're down to 92 volts. We're drawing about 10 amps. I'm sorry, let's back up. Let's go back to, I want to turn this off. I want you to hear how the compressor is supposed to work at full voltage. Okay? Unpleasant sound, but it's doing its job. Now we're going to put the extension cord in there. I'm going to leave the heater off for a minute. You'll notice the difference even without the heater on. And now let's turn the heater on. And we're going to we've dropped the voltage already to 92. I'm going to turn the compressor on and watch what those numbers do. This is the voltage, that's the amperage, and listen to the compressor. It's having trouble. 72 volts, 18 amps for the two devices. It could be that the compressor might be overloading a little bit. It's certainly not getting the cooling it needs because the motor's not spinning fast enough. So these are just some of the examples of the problems you have if you undersize your extension cords, even if you don't overheat them. Now, in the next session, we're going to take a look at this problem that we were demonstrating, and we're going to apply it to what the utilities have to deal with, electric utilities, or some of the regional organizations, like in my area in the Northwest, the Bonneville Power Administration, or in the southeastern United States, the Tennessee Valley Authority, where they don't just move electricity 100 feet, 500 feet. They move it a mile, 10 miles, 100 miles, perhaps 1,000 miles. So thanks for coming, and I'll see you next time.